Hey everybody, and welcome to our 8th video lecture. Our topic today is the fundamental theorem of line integrals. To motivate our discussion, I want to start out by thinking about a function of two variables, h of xy, which denotes the height of a hill at some location xy. So, if these are my x and y axes, and this is my hill, maybe it has a little bit of grass or something like that, then z equals h of xy, exactly grass the surface of the hill. So at any particular xy value, the distance from the xy plane to the top of the hill is exactly h of xy. We can also plot this as a contour plot in the xy plane, where here each contour represents a certain level curve of the hill. The vector field given by the gradient of h is then graphed as a collection of arrows which are orthogonal to these little contours locally. So they stick out like this. This presents us with a lovely little vector field. And now if I think about moving along the blue curve C from the starting point to the ending point and calculating the integral over C of this particular vector field, it's adding up all the various changes in height as we move from the start to the finish. So the actual value that I get is just the change in the height itself. The total change in the height itself, though, is given by the height function. So it's going to be the height at the endpoint minus the height at the starting point. And the really interesting thing about this equation is that this is independent of the choice of the path that I take, C. Because all this integral does is add up all the different changes in height. So if I go up my hill a little bit, and then I come back down again, and then go back up again, the down part and the up part will cancel. I'm just looking at the difference, the total difference in the height. In particular, if my curve is parameterized by this function r of t, then all this is saying is that the integral over the curve C of the vector field is going to be given by h of r of b minus h of r of a. In particular, it only depends on those endpoints. And this is a property in general which is satisfied by any vector field which is the gradient of a function. And remember, those are called conservative vector fields. So we have the following theorem, which is the fundamental theorem of line integral. This theorem goes like this. If I've got a conservative vector field, big F, which is the gradient, that just means it's the gradient of some function, little f by definition, and I've got a smooth curve C parameterized by some r of t, then the integral, the line integral of f over the curve C is going to be given by little f evaluated at the endpoints, just the difference there. And if you're thinking this seems sort of familiar, we can think about the analogous Calc 1 result. And in Calc 1, we showed that the integral from a to b of the derivative of some function was just equal to f of b minus f of a. So I'm just thinking about, this is just like the fundamental theorem of calculus, except that my derivative is now a gradient, and my integral is now a line integral with respect to that gradient. Let's try to actually prove this theorem. By definition, I know that the integral over C of the vector field is going to be equal to the integral from a to b of f of r of t dotted with r prime of t dt. But we can rewrite this as the integral from a to b of the sum of the partial derivative of f with respect to x times dx dt plus the partial derivative of f with respect to y times dy dt. And then by the chain rule, this is just the same thing as the integral from a to b of f of r of t, which is a function of just that single variable t, prime dt. And now by using the fundamental theorem of calculus just from Calc 1, this is going to be the same thing as f of r of b minus f of r of a. That's exactly using this Calc 1 result that we were reminded of earlier. So that proves it. And note here that we never use the fact that we're in 2 dimensions. This is going to work for line integrals in 3 dimensions too. In fact, you can define line integrals in n dimensions if you want to, and this will work there as well. So that clearly makes these conservative vector fields pretty important things. And doing the line integral of a conservative vector field is really nice for that reason, because we can do this fundamental theorem of calculus type calculation to get the answer that we want to. Let's look at a specific example. In this example, I want to think about just a huge planet here. Maybe it's got some cool continents or things like this, and some friendly life forms. Now, if we're up here in space in a particular spaceship, then the gravity that we experience from the planet causes a certain force, a certain pull on us. If our location in space is given by XYZ, and the center of the planet is at the origin, 0, 0, 0, then the force that we experience is given by the gradient of our gravitational potential energy, which in turn is given by little m times big G divided by the square root of x squared plus y squared plus z squared, where here little m is our mass, big M is the mass of the planet, and big G is this universal gravity constant. So I can ask myself, if I want to travel from some starting position whose coordinates are 2, 3, 5, and end up at some end position, say, whose coordinates are 1, 7, 9, what I want to do, and I want to follow this path, I can ask how much energy will be required. Alternatively, how much work will be done if I follow this path against the ambient force field caused by gravity. We know that the work done is the integral over c of the force dot dr. But because this force field is a conservative vector field, this will just be the difference of the potential energy at the ending point minus the potential energy at the beginning. This is a common physical thing where you hear it a lot in a physics class. It says that the work done is the change of the potential energy. But it's coming from this fundamental theorem of line integrals in this particular case. So we can rewrite our answer as mmg divided by the square root of 1 plus 49 plus 81 minus mmg divided by the square root of 4 plus 9 plus 25, or mmg times the square 1 over the square root of 130 minus 1 over the square root of 38. As we already mentioned, one of the main consequences for line integrals of conservative vector fields by the fundamental theorem of such line integrals is that they're independent of the path. So I got two paths, C1 and C2, with the same starting and ending points. We'll say P and Q. And here are our paths C1 and C2. In general, the integral of a vector field over C1 is not going to be equal to the integral of the same vector field over C2. However, if f is conservative, then equality does hold. So it doesn't matter which of our curves that we take. One immediate consequence is that the integral of a conservative vector field over a closed loop will be 0. A closed loop is something like this. It's a curve C with the same starting and ending point. Now let's imagine that I'm going around this curve counterclockwise. So I can do a line integral over C of f dr, and this is going to turn out to be 0 whenever f is conservative. One way to see this is to let this point be P and choose another point Q, and we can consider two different paths from P to Q. The first one is going to be going from P to Q following the original curve. Let's call that C1. The second path I want to consider, however, goes from P to Q following the curve C, but backwards from this ending point, so going this direction. And we'll call that C2. Since they have the same starting point and ending point, we know right away that the integral over C1 of f dr is going to be the integral of C2 of f dr. Moreover, the integral over c of f dr is equal to the integral over c1 of f dr plus -1 times the integral over c2 of f dr. And the minus sign is coming from the fact that it's the same curve, but the direction is reversed. So that puts a minus sign in front of the integral. And because these two quantities are equal, their difference is going to be 0. So the integral over that closed curve is 0. Another way to see it is we can just remember our fundamental theorem for line integrals, which is going to tell us that the integral over c of f dr is going to be given by the value of the function for which f is the gradient of, evaluated at the endpoint, minus the same function evaluated at the starting point. In this case, the starting point and the ending point are the same, so of course we get 0. In fact, what we've shown is that a line integral over c of f dot dr is independent of path if and only if the integral over every closed curve is 0. In fact, we can prove the more general following theorem. These are all equivalent to the idea that f is conservative. Let f be a continuous vector field on an open connected region D. Then the following are equivalent. F is conservative. The integral over c1 of f dot dr is the integral over c2 of f dot dr for all smooth paths in D that have the same starting and ending points. So this is independence of path. Or the integral over c of f dot dr is 0 for all closed paths in D. Let's try to prove this. We've already shown how 2 and 3 are the same thing, because we can break up any closed loop into a couple of smooth paths with the same starting and ending points, and vice versa. Given those two paths with the starting and ending point, we can create a new loop, which is a closed loop. Furthermore, we talked about how if f is conservative, then it will be independent of path. And that's just a consequence of the fundamental theorem of line integrals. By the fundamental theorem of line integrals, the value of the line integral will only depend on the endpoints. It won't depend on the path that we take to go from the start to the end. So the only thing that we're left to show here is that 2 implies 1. That is, I want to show that if I've got a vector field which is independent of path, that it has to be the gradient of some function. To do this, what I'm going to do is I'm going to think about my domain as being some sort of set here, D, and I'm going to pick a starting point P in here. And once I've picked my starting point, I'm going to define a function, f, which for any value q is defined by taking a line integral over our curve C from P to Q of f dot dr. And I know that this is a well-defined thing because it's completely independent of the curve C. So let's just define some function. My claim here is that f is differentiable and that the gradient of f, in fact, is my original function, my original vector field, big F. So we need to try to show this. Well, to do that, what I'm going to do is rely pretty heavily on the idea that I can choose whatever path C I want to in order to calculate what f of q is. So let's look at that picture again. And what I can do is I can choose a path which curves up and then goes straight to Q after a certain point. Let's call that point R, and let's let Q be the point xy. Then for any h sufficiently small, I can look at the value of the function f at the point x minus hy. By definition, this is the same as the line integral of big F along the curve which follows the orange curve, but stops at the green point. Let's call that curve C2. Let's call the original curve C1, which goes from P all the way to Q. So I know that f of x minus hy is given by the integral over C2 of f dot dr, and f of xy is given by the integral of C1 of f dot dr. So the difference is just going to be the value of the integral over c1 minus the integral over c2, which is just the integral over the difference in the path. Let's call that c3. But on the part c3, I know the path is completely horizontal. So c3 is parameterized by r of t equals x minus h plus t, comma y for t between 0 and h. So the difference now can be expressed as the integral from 0 to h of f of x minus h plus t y dotted with r prime of t dt. And we should note here also that r prime of t is just going to be the vector 1, 0. So we can write f of xy minus f of x minus hy over h is equal to 1 over h times the integral from 0 to h times f of x minus h plus ty dotted with the vector 1, 0 dt. And if I take the limit as h goes to 0, on the left-hand side, I'm getting the gradient of little f at xy. And on the right-hand side, I just end up with f of xy dotted with the vector 1, 0. So little f sub x is just the x component of big F. By a similar argument, we get that f sub y is going to be equal to the vector field dotted with the vector 0, 1. It's the same argument as before, except that the path that we're going to take from P to Q is going to do something where it goes horizontal for a bit and then goes completely vertical at the end. So if we put all this together, I get that the vector field has x component given by f sub x and y component given by f sub y, which is just the gradient of little f. In particular, it's conservative. So this is a really nice sort of characterization of what a conservative vector field is. It's a vector field which satisfies one of these following properties. Either it's independent of path, or it returns 0 whenever I integrate over a closed path. Of course, it's really hard to check if a vector field is conservative that way, because I can't check every integral over every possible closed path. There's just too many. So we'd like to have some other sort of better way to check if a vector field is conservative. So our question is, how can I test if a vector field f is conservative? Well, I know I can write down my vector field f in ij notation as some function p times I hat plus some other function q times j hat. Now, if f is conservative, then we know that f is the gradient of a function little f. That means that p would be partial f partial x, and q would be equal to partial f partial y. But that means that partial p partial y is going to be partial squared f partial y partial x. And by Clairaut's theorem, this is going to be the same as partial squared f partial x partial y. Like, the mixed partial derivatives agree. We learned that earlier. And that's going to be the same thing as the partial derivative of q with respect to x. So the condition that should be satisfied in the case that f is conservative is that the partial derivative of p with respect to y should be equal to the partial derivative of q with respect to x. So this is a really nice way to check if a vector field is conservative or not. In fact, as long as p and q have continuous first-order partial derivatives on a domain which is of interest, which is sufficiently nice, this will be an if and only if statement. So f will be conservative if and only if the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x. Let's summarize that with a theorem. If f is pi plus qj, and p and q have continuous first-order partial derivatives, then if f is conservative, we already showed partial p partial y equals partial q partial x. And this is true on a domain D. By a domain, I just mean some sort of open subset of the plane. The converse is also true if D is simply connected. That is to say, on a simply connected domain, the partial derivatives of p with respect to y equal to the partial derivative of q with respect to x implies that the vector field is conservative on that domain specifically. Here, by a simply connected domain, we're thinking about domains which look like this. In particular, it's connected, and there are no holes. So some examples of things which are not simply connected would be something like this, where there's two parts and it's not connected at all. Or something like this, where I've got a hole in the middle, and this is connected, but not simply connected. So it's important here that in order to have the converse statement, where these mixed partials agreeing implies that the vector field is conservative, we need to not have any holes in the domain that we're curious about. So we can think about an example that we talked about last time. The vector field f of xy equals minus yx, which gave a sort of windmill pattern. In this particular case, p is minus y, and q is x. So I can check that p sub y is minus 1, but q sub x is equal to 1, and these are not equal. As a consequence, I can conclude that f is not conservative. Conversely, let's consider the vector field f of xy equals 3 plus 2xy, x squared minus 3y squared. Again, the first entry is p, and q is the second entry. And I want to ask the question, is this conservative? Well, I can check that partial p partial y here is going to be equal to 2x, whereas partial q partial x is equal to 2x also. So this will in fact be conservative. Let's actually try to find a function whose gradient is f. To do this, I can use a little trick called partial integration. So what I'm going to do here is I'm going to remember that if the gradient of little f is big F, that's going to say that p should be little f sub x, and q should be little f sub y. So if p is little f sub x, then if I were to integrate p with respect to x, I should end up with f again. But because I took a partial derivative, I need to do a partial integration. And what this means is that when I do the integral in the very end, I'm treating y like a constant, but I should have an arbitrary function of y in the end rather than an arbitrary constant c, because my derivatives are really partial derivatives here. So this is the integral of p. P here was 3 plus 2xy. So I'm doing the integral with respect to x. This is going to give me 3x plus x squared y plus an arbitrary, not arbitrary constant, but an arbitrary function. Let's call it h of y. And what I've used so far is I've used one of my two equations, specifically that p is f sub x. To figure out what actually f has to be, I need to figure out what this arbitrary function is. So I need to use my second equation here to do this. q should be equal to f of y. And now that I have this wonderful expression for f, I can take its partial derivative. So this will say that f sub y is equal to x squared plus h prime of y. However, f sub y was supposed to be q. So we can write that q should be equal to, well, what was q? Q was equal to x squared minus 3xy. So what we get here in the end is that x squared plus h prime of y should be equal to x squared minus 3xy. Oops, I've completely written down the wrong q. Q was x squared minus 3y squared. What a silly mistake. There we go. That makes a lot more sense. So we get x squared plus h prime of y equals x squared minus 3y squared. So if I cancel off the x squareds, I get that h prime of y is equal to minus 3y squared. So if I just integrate that, that tells me that h of y is going to be equal to minus y cubed plus an arbitrary constant. And that's a usual integral because that's a usual derivative. So what f had to be was given by 3x plus x squared y plus h of y. So 3x plus x squared y plus my h of y, which is minus y cubed, plus a constant. And this is a function whose gradient is big F, and you can even double check that at that point. Alright, so that's good enough for now, and I'll see you guys next time.